Okay, hi everybody. Good day, good afternoon, good evening, everyone. This is a great opportunity to speak with you today. We'll be talking about variants. My name is Roy. I'm from Israel. I live in Tel Aviv. I've been doing C++ for more than 20 years now. Currently, I work for Istra Research. We're a financial company doing low latency trading in Israel. If you enjoy doing complicated things in software in C++, and you're in the Israel area or want to come to Israel to work, then please feel free to contact us. This is my first time at CppNow. It's been really great so far. I've been seeing a lot of CppNow talks on YouTube in the past, and it's all great. And I'm really happy to be here today. Throughout this conference, I've been trying to be as active as possible in chat and in Q&A, and I really encourage you to also do that. Please feel free to ask questions, to make comments. Let's try to make this as productive as possible for all of us. And I'll be happy to learn and hear what you have to say. Okay, so today, as I mentioned, we'll talk about variants. Variants is a feature that was added in CPP 17. It's really a large advancement in terms of the way we can write our code, and I'll try to give you a short introduction of what it is, but I assume that because it's a long time part of the standard, you probably know pretty much what the variants are. So after a short introduction, I'll dive into the ways that variants are currently used and used around various places online and in libraries. And after that, I'll dive into some examples and the new ways or new techniques that I've been using for variants and for these types of objects around the code bases that I've seen, and potentially, hopefully, some of the approaches that you'll see, you'll also like and want to use as well. So let's dive in and talk first of all about just the pure basics that you probably know. So a variant based on cppReference.com is a class template that represents a type-safe union, okay? And Boost.org also says that the variant class template is a safe, generic, stack-based, discriminated union container, okay? So in plain English, it's a union that knows or holds its type. I assume many of you know what the union is. That's a legacy part that C++ has received all the way from C, and it's a way to basically contain either of several types of data in the same storage location. You can see that in C we could have a union with two different types, and any function or code could go and access whichever type they like, although only one is actually active at any point in time. And C++ variant parallel to that is this template class that's templated on the different types that it can hold. And we can either use the get accessor to access the specific member that we want, or use some visitation mechanism, which is like std visit, to go and access the item, whatever type is in there. So that's the basic thing. And the key behind the difference of a union and a variant is that the variant is much safer because it knows which of the alternatives it holds at any point in time, and it will not let us make mistakes and access a different member when it's not the right one that's currently in use. So just to, again, put us all on the same page, struct or a tuple, those are what are sometimes called product types, where different members or different objects inside a struct or a tuple are held in parallel, one next to each other. Okay, and sometimes they're also like padding in memory, whereas a union and a variant are basically some types where it's just one member or the other, but all occupying the same place in memory. And as we mentioned, the variant also knows its type, so there's extra memory that it uses on top of a union to hold what we call the tag, which keeps track of the exact member that is currently active, currently in use. That's the basic thing. And why do we use it? What is it good for? So if you try and look on the internet, online, around code bases and previous talks in other conferences, You can see several use cases that are typically discussed when variants are mentioned and when variants are commonly used. So there are state machines, there's the use of value semantics, and other various options. Let's go quickly one by one to give you a short sense of what each of those are. So state machines, basically we might have learned about state machines in university. If we learned computer science, it's also something that is quite easy to understand. It's basically an object that can have a separate state and different parts of its life cycle. And variants are really tailored towards these types of things. And here we can see a talk or a screenshot from a talk from meeting C++ 2018, where a state machine for a video game is described. And we can see that the state is uses a variant to basically dictate that the game is either in the circling mode, fly to center, etc. And each of the states has a different variables, different information that needs to hold and manage while we are in that state. Okay, here's a talk from CppCon by Mateusz, who's attending this conference right now, who's also gave a nice long introduction of how to use variants in different ways. And he also made the point of showing that it's quite common to use variants when you want different types of events, different types of states to occupy the same area in memory and to be moved from one place to another. This might be a good place to mention that the fact that the variant holds its memory for each of the members means that we can be dynamic but still stay on the stack. Okay, so usually if a variant we use it as a local variable, it lives on the stack. We can move it and copy it just like a value. It's what we call value semantics, an opposite to dynamic or reference semantics. And it can be very easy to this way move around and reason about the states of my object and not hold the burden of using pointers, memory allocations, etc. Commands is another use case that's pretty common, simply because of the fact that the command is usually a pattern where we want to move information around from from one object to another. So the fact that variants are value semantic based objects that can be moved and copied easily without concern of memory management, etc., makes them really easy to think about. And here in this talk by David Senkel, he also gave some examples. And again, we can see that command can be either set score, fire missile, fire laser, etc. Again, a nice theme from a video game. And this single command is just basically a block of memory that can be stored, copied, etc., just like any trivial value in C++. If we move on, we can look at another separate use case, which is sort of like maybe a trivial or a narrow choice of a variant where we only have two alternatives. One is like the good path alternative, and the other is an error or an exception. Here's an early talk from 2018 where Andrei Alexandrescu basically gave his thoughts about the importance of something like expected, like a type that can either be a success or a failure. And when he went and described it, he talked about variant being one of the motivators or one of the background technologies that pushed him towards trying to get expected into the language at that point in time. Another such narrow case for a variant is optional. Optional is a variant that is either one alternative or nothing. Okay, so if you have something that's either there or not there, optional can be used, and it was also added to the standard in CPP 17 STD optional. But to a large extent, it's a refinement of variant. And this talk from the last CppNow by Nevi Lieber is also a great resource if you like to learn more about uses for variants and how they came to be, and there are many intricacies of how to use them and their design as well. Next up, we'll talk about runtime dispatch. Runtime dispatch is potential replacement for things like virtual functions and virtual inheritance, where a variant can hold many types, but if all the types basically have a similar interface and implement similar functionalities, then we can use them instead of creating a class hierarchy, and won't need to suffer all the, I guess, complexities of needing to define the hierarchies in advance, needing to perform memory allocations, dealing with deallocations, etc. And this talk from CppCon 2019 in Bal showed how STD visit could be used for just that motivation. She also gave good benchmarks into the performance and what are the pluses and minuses in terms of runtime for using STD variant and visit compared to other alternatives such as virtual function calls, etc. Later on in the MOOC++ meetup, which is a great meetup that you're welcome to join, Klaus Egelberger also gave a nice in-depth, I guess, overview of various types of doing runtime dispatch, and try to compare all the different types and one into on various categories and various criteria, and give some scores. As we can see, the visitor, which is a variant, and also Michael Park's variant, which is very similar, has received very high scores across the board compared to other mechanisms that existed in C++ before. And that might be a good motivation if you're considering runtime dispatch to look at variants as a good or a potential alternative for what you might want to do. Moving on, the last really big and really large material and focus around the usage of variants is around what we now call pattern matching. And pattern matching is basically a mechanism to try and also do some dynamic dispatch and things sort of like switch statements with different types of objects, similar to dynamic dispatch. And if you look deeply at the slide, you can see that Michael Park here, who's one of the lead developers of the STL variant implementation, and he's a contributor also to pattern matching in C++. He's shown that the typical visit many times has like many different cases where it looks at the different active members that can be inside a variant, and also inside each alternative, many times we'll do some destructuring or structured bindings to extract the members of the specific alternative and work with that alternatives. And basically, Michael also went and showed us that this type of usage of visit is quite common and quite important on one hand. But on the other hand, it's very lacking, and that isn't as powerful as other languages have things that are similar. He also went on and gave us this screenshot from a bit-bashing article that basically said that STD visit is claimed to be everything that is wrong with modern C++. So I think, and Michael also says that the visit itself is very complicated, very cumbersome. It doesn't have all the capabilities that full pattern matching has. And variants themselves are a very good part of modern C++, but STD visit is lacking, and there's reason to go and improve STD visit, but keep variants as they are. If we'll riff more on that topic, there's also a section about that in Nevin Lieber's talk, where he also mentions the importance of pattern matching, and the fact that the first variation on STD variant wasn't very, wasn't considered, as pleasant as it could be. And this in his slide here, there he has a picture of Strausrup, and he basically mentions the large desire from the committee to not stop with variant as it was in the C++ 17, but also go ahead and implement more functionality such as pattern matching later on to come. And the pattern matching is actually planned to be soon with us, and hopefully in some close by future edition of the language. And quite recently in a talk that Sean Parent gave on February this year in the ACCU conference, he also talked about pattern matching and its importance. And this slide, I think, can give you a short primer on what pattern matching aims to do in comparison to other features that have to do with the way that functions work in relationship with the values that they're given. And as we can see here, Sean basically contrasts three hypothetical lines of code. The first one is using concepts, okay, and he wrote some pseudocode that tries to create a template that's templated on maybe a value type that at compile time will only get instantiated and will only be relevant if, for example, the value is non-negative. Contracts is another feature that was aimed to enter C++20 and has been delayed. We will likely enter or progress in C++23, where we do a runtime check instead of a compile time check, and still try to either assert or alert or make some validation of a contract that makes sure that in runtime the function f will not be called with a negative value in this case. And the last line is pattern matching, where it's sort of like a mix of both worlds. It's not causing a failure and blow runtime away, but just remove the specific function f in this example in case that the condition is not met. So very similar to concepts, but instead of doing that at compile time, they're doing it in runtime. That's the basic idea behind the pattern matching. And because this is such an important topic, I'd like to dive deeper and give you some more examples on how it's meant to be in the future version of C++. So here are a few slides and screenshots from the current proposal for pattern matching. I should say that pattern matching is still not in the standard, and the current priorities for C++23 has put it in the second tier of importance, meaning that there is no strong expectation that pattern matching will be part of C++23, but there is a strong desire to move this forward. And if it won't be getting to C++23, at least there's currently a desire to put it or to add it maybe to C++26 or something like that. So this first example is quite easy, quite trivial, but basically shows us that in the proposal, there's a new keyword, a new functionality called inspect. Okay, and to start things off, inspect is very, very similar, can be thought of very similar to a switch statement. Okay, and these two code pieces in the left and right should have the same functionality, just different notations. Yeah, so instead of case statements, we just put values and we use this arrow operator. And instead of a default, you can just do a double underscore. Okay, but this is just scratching the surface. We can also go deeper and combine the structured bindings into the mix and the destructuring. So we know that we can access members of structs, tuples, and there's a contract of pulling out members of various objects using the structured bindings. And with the inspect keyword, this destructuring can happen automatically. And the conditions that we write in our cases for inspection can actually be broken up into the different members. We can either put constant values or dynamic values, and in this case we can see that we can use inspect to very concisely run the different code based on the values that we receive in our pair. And certain code will run on certain values and others on different ones. Another thing that we can see here is that the code on the left is an if-else code block, and the order matters. Okay, and on the left, if we were to reorder the if statements in a different order, the entire functionality can change, because and it's important to start by looking for the most specialized or more specific scenario, and then move to more generic ones down the if-else chain. And the inspect will also likely work in this same manner. So there is importance to the ordering of the different legs or branches of the inspection statement, and we should keep that in mind when we write inspection code. And this is all the uses of pattern matching when we're basically choosing what to do based on values. And the other cool functionality for variants and for inspection, sorry, is that it can also work based on the types, on the active types of variants. So if right now we use the visit function in order to choose specific operator overload based on the active type of variant, inspect can be used in the same manner, again with this notation like the angle brackets to choose the specific alternative that we want. And this is basically a more terse and more a language mechanism instead of a library mechanism. And by itself, it doesn't look like much of a difference from the current STD visit, but the power lies in the fact that you can do a lot of mix and matches between the value-based inspection and the type-based inspection and go even deeper. So that's the way that it is. So in a nutshell, the inspect statement is sort of like the C-style switch and STD visit and structured bindings all combined together to one single construct. And with that combination, we can get much more powerful ways to describe the conditions that we want to choose where to go and what code to run by. And the inspect mechanism knows how to extract members out of tuples, variants, even STD any, and can do any cast operations. It can look into polymorphic objects and understand the type hierarchy and choose derived classes versus base classes, etc. There's also a lot of room for customization by writing your own extractors and matchers in order to help inspect know how to break up and destructure your own objects and classes, and how to create various complicated conditions that can be matched through. As I mentioned before, inspect works by matching the first match that seems to satisfy the runtime condition. There is no like jump tables usually, or if the compiler chooses to implement a jump table, the compiler can do it, but the semantics will be as if it was a first match. Inspect is also sort of recursive in the way that it inspects. So if I have an object that contains other objects, a single inspect statement can have a recursive condition, and we'll see a nice example in the next slide. There is no fall through by default. I think there's no fall through at all across on the different legs of an inspect statement. And there's also an attribute called strict that is proposed to be used to allow the compiler to help us and tell us in case we create an inspect statement that doesn't cover all the cases. So if I have an inspect statement and I don't have like an underscore or default alternative at its end, the compiler can try to reason and see if all the different legs that I put inside the inspect statement really cover all the cases that are possible in the input. And if not, and I use the strict attribute, the compiler should try and assist me and tell me that I might be missing some cases. As mentioned, pattern matching is a second-tier priority for CppNow. As far as I recall, there are, I think, 3 or 4 features that are top priority for CppNow. One of them is executors, I believe. The other is I think additional conceptification of the STL library. I don't remember all of them, but in the second tier, there are 3 other features. And as far as I recall, pattern matching is one of them. I believe contracts is also on that same level. So the assumption is that it might not enter the language of CppNow, but there is a strong desire to make progress on this feature. And before we let pattern matching go, this is like the big like motivating like a cool factor slide that can show you like a lot of the full power potentially of using pattern matching. And here we can see a rebalancing of a redback tree that's done in just a few lines of code of inspection. So in this slide, the idea is that we have a binary tree of nodes. Every node has a type or an enum that says whether the node is black or red. It has two shared pointers to the left and right children of the node and a single value. And here we can see that just this first leg tries to cover the case where we have a black root node which has a child or whose left child is red and whose left child is also red. And those are the cases I can give names to all the different values across the tree and create a different, more balanced subtree. Okay? And each of the four legs here cover all the different modifications that needs to be done for rebalancing the redback tree. And here we can see rebalancing of a redback tree done in just a few lines of code. A few interesting things to point out in this slide is first, as we mentioned, the recursive or hierarchical nature of inspect, where in one single condition, we can look not just at the root object, but also at its children and grandchildren to that effect. And secondly, we can put some constraints that check whether to even go further with recursive checks, etc. And in this case, the star question mark construct is basically what makes sure that you won't, by mistake, dive into through a null pointer and get a null pointer problem. So this inspection will only find nodes that are at least of depth 3, and they have both a red child and a red grandchild with a full set of other children and grandchildren. It will not be matched if at any point inside this subtree, or in the cases where we're looking, we find a null pointer that might lead us to get errors. So this is all quite cool. If you have more questions on pattern matching, feel free to ask in the Q&A or in the chat. I'm not an expert on that, and I strongly suggest you also go and see Michael Park's talks on the matter, but I think it's really cool. Okay, so that was a short like overview of both what variants are and where they're where they are most commonly used right now in the world. Now I'll try to take a look at a specific use case, which has to do with the connection between variants and unions. Okay, so let's try to remind ourselves what the differences are, and why they're important. So basically, the root source of the strength of a variant is the fact that it has a tag, and the tag is private. Okay, because of that, there is no way for any outside code to mess with the memory layout or the memory inside the variant and to change the active member without changing the tag along with it. So only the constructor and the assignment operators or in place of operations of variants can actually access the member inside the variant and change it. And if they do, the tag automatically gets changed, and it means that there are no chances of user errors, and the compiler knows that all the possible alternatives for the tags. There's no way to put some invalid value inside the tag, and for that reason, there's a lot more power, and it's a lot safer and much better ways to make sure that we don't make harsh mistakes. So here's an example of old C code that uses unions and not variants, where mistakes exist. And I guess I can let you look at this code for like 10 seconds to see if you can spot some of the mistakes that I've put in here. And I should just mention that this is like perfectly legal code that compiles in C and C++, or it's legal in like in terms of compilation, there's a compiler will not generate usually any error for this case. Some compilers will generate warnings, but not all of them. It's not mandatory. But still, if you go and run it, it will have bugs. So what issues exist in this code? So first of all, we can see that when the object inside my union is a citizen in this case, I go and access id.passport, which is probably not what a person intended when they implemented the check ID function that accepts a union as well as the type of the union. Similarly, it's easy to forget missing types. Okay, if my union also has a third alternative, which is the factory certificate and the robot type, and the switch statement doesn't mention that type, and this is not a problem in C++. In some cases, like when we use an enum or enum class, the compiler can warn us about it, but not much more than that. And the third thing that I want to mention is the fact that there are no break statements here. It seems quite clear that the intention was to break and not fall through between the different parts of the switch statement. So this is all risky. And in the C++ using variants, all of these risks really are gone. Okay, we just instead of a union, we can create a variant of the three different types. In terms of memory management and of usage, it's very, very similar to the union, but it also keeps the tag together with the type itself. And this way, the check ID function can just accept the single argument, which is the variant. And in the C++ manner, we can implement like a single like check method for all the types and use a generic lambda and just visit and perform the check to all the different types. And the compiler will let us know and will not compile the code if one of the alternatives of the variant doesn't have a check method. And we are sure not to make a mistake and call a specific check function for the incorrect tag that is currently in place. Okay, so that's the core, the root reason for the safety of variants and why writing a variant in our code and migrating from C-style switches into variants can be very, very helpful to make our code safer, clearer to read, and help the compiler help us. Okay, but the example that I gave before is a nice example, but I have to say that it's in many senses a straw man. Okay, when people actually write unions in C, they don't really do it like that. They don't really have unions just being passed around alongside their tags as separate variables. The typical thing to do is to put the tag together with the union and pass them around as a single struct, very, very similar to variants. Okay, so a typical C code struct that uses a union might look like this, where I have like an identity card. It has a type member, and then it will be followed by a union of the different alternatives that can be used as an identity card. And this entire struct will usually be passed in C together from one place to another, just to make sure that we don't lose track. So this safety, it's not mandatory in C, but C programmers usually you do it this way. There's another alternative of writing similar code and creating similar memory layouts, which is to put the common type as not outside of the union, but as the first member of each of the union alternatives. Okay, so in this case, we have you can see that the union is a union of three different structs, but all three structs actually have a similar prefix. They all start with the type. Okay, and this is an alternative approach to the one above us in terms of memory layout. It is exactly identical, and one can think of pluses and minuses or advantages and disadvantages to one of these approaches compared to the other. I think a large advantage of this second approach is that if a function does, for example, have a pointer to a citizen or receives a citizen specifically, it can also look and have access and visibility to the type itself. Okay, this is seems a little not necessary in this case, because obviously if I have a pointer to a citizen, I should know that the type has to be a citizen. But over time, the header can get more information, such as maybe as the expiration date or a photo, things like that. And in those cases, those fields, they're shared across all the different identity cards, but still I want to have access to them, even in code that knows that specifically a certain alternative is the one that it's working with. And for that reason, it becomes, as time goes by and as these structures get more complicated, I think people move from the explicit header model to the implicit header model. And in C style code, you will sometimes see idioms such as this one, where we use the preprocessor, like define the header fields, which are the common prefix of all the different alternatives. And then the header structure will be only the header fields, and the different alternatives will start off with containing the header fields and continue on with the specific members of the types themselves. And the union, can access each of the different types. And I know that because of the common prefix, it's okay to access the type before even knowing what the active type currently is. So that's the way it is in C, and that's the way people commonly use these types of things. Yeah, and I have to say that I don't know if this header fields thing looks familiar to you, but if you squint a little bit, you might try to convert the open curlies here into maybe a colon, and try to make this look a little bit maybe like a C++ to some extent. Okay, so this is the way that things are done in C. And when we go and work in C++, we can obviously abandon it all and use std-variant, but there are some cases where keeping the C memory layout is actually important. Okay, the C memory layout as it is right now is in many places considered sort of like a standard. Okay, there are many protocols and file formats that are very, very used to defining things or binary structures and binary records as headers followed by different members, where the header might be a selector, or based on the header values, we know which actual members follow. We see that in the TCP/IP protocol. In finance, we see it quite commonly. There are also like file formats that use this mechanism in their headers and in the information records. Many serialization libraries that aim to serialize any object they want to give it usually support sum types and unions, and they usually work by serializing the tag, followed by the serialization of the specific members of the active tag in use. And for that reason, even when we work in C++, we sometimes need to consider this memory layout because it's so common. Not to mention that if the code base that you're working with already uses unions and has these types of C layouts, it might make sense for you to gradually migrate from unions into variants maybe, or from the legacy code into modern code, and still try to keep the memory layout the same. And just for the sake of doing compatibility, binary compatibility, and making sure that we can pass binary objects from one place in the code to another, although some of it may be legacy. Okay, so one goal that I'll try to reach in the next few slides is to write some C++ mechanism that will be safer than the C unions, but keep the memory layout and the design as it is right here, and not break the desire to move all the way to the safety of this private tag that no one can control and no one can look at. So this is the idea. And before we dive into my suggested implementation, I want to talk a little bit about this notion of compatibility and memory layout, and what C++ has to say about how legal and how well-defined it is to look at network protocols and map them directly into structs, into unions, etc. So the C++ standard actually says that there are many cases where it's okay to have a pointer to this to a union or to an object that has these header fields, and having the pointer not accurate enough and not look specifically at the actual type of the object that it's pointing to, and still access the header fields in a perfectly legal and perfectly well-defined manner. It's not always undefined behavior to look at an object of type X and try to access it using like a reinterpret class as if it's type Y. And the rules have to do with a notion in the C++ called the standard layout. Okay, so every class instruct in the C++, it can be a standard layout or non-standard layout. Standard layout is an attribute or a type trait that is part of the standard. And basically, the standard says that the standard layout classes are useful for communicating with code written in other programming languages. So this notion was deliberately added to the standard in order to allow binary communication with other programming languages, with other pieces of code. If a class is a standard layout, then all compiler implementations have to abide by the same rules of how to put the class in memory. And if that layout, in this way, I can have a class compiled with one compiler, have binary compatibility with classes compiled with another compiler in the same scope of work. So this is the importance of standard layout. And the compiler has quite a lot of rules and constraints about what one needs to do in order to make sure that the classes that they write is in fact standard layout. So the most important things to remember is that standard layout classes cannot have any virtual members. If you think about it, it kind of makes sense because virtual members usually hold the virtual pointer, VPTR, which is something that is not meant to be cross-language or cross-compiler safe. There's another rule about the access control. All the members have to have a single access control. Either all members are public, private, or protected. You cannot mix and match and have several members that are protected, others that are public, etc. The reasoning behind that is basically to allow different compilers to adapt different rules on how they place members in memory if they have different types of access control. But the standard says that if everything is in the same access control, then things are standard layout, and there is it is mandatory for all compilers to put all the members in this very, very specific arrangement in memory. And the third constraint that might be important to understand is that it's okay for a standard layout class to have class hierarchies and to have base classes and even multiple base classes, but it's not okay for the different classes in the hierarchy to have non-static members. So all of the non-static members of a class have to reside within a single class of the hierarchy. So if I have a class that is a standard layout and has non-static members, it's certain that all of the base classes it derives from have no members, no non-static members. All its members have to be static. And similarly, if there is a standard layout class and I derive from it, then I will also be standard layout if I do not add any non-static members. Okay, so these are the rules. And C++11 also gave the STL a mechanism where one can check at compile time whether a class is a standard layout or not. So is standard layout is a type trait that can be used in compile time, and the compiler will tell me if I'm meeting the rules or not. In C++17, there was they added syntactic sugar that many of you already know, the _v, but not much more than that. And one of the things is that it's not only that if I have a standard layout object, then it's really mandated how the memory layout will be, and I can work across languages and across compilers. It's also legal to access members without really knowing the type, as I mentioned. So here's the quote from the standard. In a standard layout union with an active member of struct type T1, it is permitted to read the non-static data members of another union member T2
if this member M that I'm trying to read is part of the common initial sequence of T1 and T2. Okay, so there's a definition of a notion of an initial sequence. So every standard layout class can, all of its members are ordered. And if two different standard layout classes have a common prefix or common initial sequence, then I can access the members of one of them, even if my pointer is a pointer that points to the other. Okay, and in C++20, we also received another type trait or a mechanism that we can use to check, which is called the is corresponding member. The is corresponding member is a compile time context per predicate that basically receives two members of two different classes, and it will basically be true only if it's okay to access one type if I have a pointer to the other type. Okay, so it basically checks whether the two types are of standard layout objects that have a common prefix all the way through to this type member, and the member is of the same type. If one of them is a char and the other is an int, is corresponding member will return false, etc., etc. So the compiler will let me know if I want to, and let me check if it's okay and legal to go and access a union using some header pointer before actually going and actually doing the correct reinterpret cast into the correct alternative or the correct active member that's in there. Okay, I hope this is understood and makes sense to all of you. But basically, this framework allows us to basically use unions instead of variants and get some safety and still be standard conformant. It is okay for us to use a C-style union and still be legally, it will be legally okay to go and inspect one of the active members without even knowing what it is. So Intrusive-Variant is the solution that I propose. Okay, so it's a library similar to a variant, but instead of having the tag outside of the union memory block, it is inside. It's intrusive. Okay, so in this example right here, we're going to basically have a safe alternative to this C-style code here on the right, where I have you can see a union of three different objects, basically a citizen, a tourist, and their common header, and all of them have this common prefix. Okay, the first member, which is the const ID type, is a common prefix. And for that reason, it's legal to work with that type of union. But instead of defining a union, I'll go and use an intrusive variant. So the intrusive variant, I will go and need to tell it what's the type of my tag. Okay, what offset it is from the start of the object. Okay, the offset in memory. And after I tell this information to the unit, I basically tell it where it can find the tag. Then I go ahead and add the specific active members or potential members that can reside inside the union. So here I can say that I want to have two different alternatives. One is the citizen, the other is the tourist, and I will use the citizen when the ID, when the tag has this enum, and the tourist when the other enum will be used. Okay, so this basic notion is a library that can replace the different the C-style union is more verbose and makes sure that things are safe, and we can use this intrusive variant similar to the way that we use standard STD variants and get a lot of the safety. Another approach of creating this same variant is to basically add a few static context per tags to the alternatives. Okay, and then I can use like another like helper, which where I only there's a small typo here, but where I can put either the citizen or the tourist inside my variant, and this helper will deduce or try to find out the exact tag value for each member by looking at this context per tag. So that's the basic idea, and this makes things a little more easier to understand and more concise and less error prone. So as we can see, the user dictates both where the type resides inside the memory region, what its offset is, it also the user also dictates the exact tag value that corresponds to each of the union alternatives. And once we do that, we can still use a visit. Okay, it's not std visit, but it's a very similar visitation function that still works in O1 complexity by using some jump table or lookup table. It can be larger than for std variants because the jump table is not for consecutive small indexes. It can be for larger indexes, but it still can be a constant time complexity. And this class also allows some more customization points for deducing the types. It's not just putting a context per member here or placing the values inside the variant tag type alternative. There can be other ways of doing this deduction through customization points. Okay, so I hope this notion makes sense to you, and I hope it sounds like something that's interesting to be used. And as mentioned, this is the same memory layout as we had before, the same type of accesses, but we can go in once we have this object, it's much easier to go and inspect the types, to know that we're not making any mistakes, and to use visitation-like things with all the safety where the compiler will tell us if we accidentally forgot one of the alternatives, etc., etc. I should also note, by the way, that since we're in C++ and the const matters more than in C, the addition of making the ID type const also helps to ensure and to make it less likely that someone will go and pollute the memory region and put a type that is not one of the types that we declared in compile time for our variant. Okay, so that's intrusive variant, and I find it helpful as a way to migrate from C-style code into C++. And getting the tag, as we see, needs to have the library know which offset, where to look inside the memory region to find the exact tag. And the basic way to do it is by using something like the offset. So a get tag function could receive like the header object or like one of the alternatives. As we mentioned, as long as the tag is part of the common prefix, then it's totally legal to use any one of the alternatives as the root object that we go in there and use to access the tag member. And using the offset of, I can basically find the exact offset in bytes into where I want to look. I need to look to find the tag itself. There's potentially I can either want to use offset of or maybe integral constant, just in case I have a templated code that needs to work with integral constants. But there are maybe other ways that I can use in order to get and put my hands on the exact tag. So one of them is to just pass the pointer to the member. Okay, so the get tag function, I can also just accept a pointer to a member and just access that instead of having it the offset in bytes. Okay, I think it makes more sense. It's sometimes easier to read. Or similarly, we can go and maybe call a member function. Okay, so we can make our intrusive variant templated not on the offset, but maybe just give it a member function, and we'll go and call the member function in order to get the tag of this specific union and know what the active member is. Okay, this using of member functions can be very, very strong in various cases. First of all, it's useful in case the tag is private. As we mentioned, standard layout means that standard layout means that all members must either be all public or all private or all protected. But if one goes and makes their union such that all the members are indeed private, then it makes things even more safe. Then they just need to add some public accessor methods, and here we can use this method in order to get things to work. In terms of the code bloat and performance, I have to say that it shouldn't be any larger in memory, because again, the memory layout of the variant will still be just the union and one object of the ID type of the tag. Okay, I am templated on the specific way on how I go and fetch and get the tag from my object, but not much more than that. The code size or this memory layout stays exactly the same. Another reason why using pointer to members, pointer to functions can make things more interesting or more important is when my tag is actually not an exact object or member inside my class, but is calculated. So, for example, I might have a few members inside my header, and the actual tag or actual active type is something that's only deduced by looking at the relationship between some of them. If perhaps if the first member in the header is larger than the second one, it means that I'm in one of the alternatives. If it's smaller, maybe in another alternative. So if the protocol is more complicated, I can use a member function to basically look at the header and give me just return the type that I can use to understand what the active member is at that point in time. Okay. Another form of accessing the member is using a free function or a lambda. Again, this is less intrusive. Again, if I have the structs and the unions as something that maybe I include from some shared code base, it's in C currently, and I don't have the luxury of really accessing or changing the types, and I can define lambdas as another approach, another way to get and understand the actual tag of the active members. Okay, so I hope this makes sense. I see that there's more discussion in the chat about the memory layout, but I think I'll maybe try to go and get back to it later on. Okay, so how would you do this tag extraction? I just put this short snippet of code here to give you an idea, because I think it's really cool. At least the second alternative is really cool. So the first one, the first implementation of getTag, you see using C++20 concepts to work with anything that's convertible to a size t, things that are like offsets, and the integral constants are also convertible to size t. And basically I go and use a reinterpret cast. Okay, so I reinterpret cast my object to called char, add the offset, and cast it back. So that's basically the way I do it. The other alternative is, I think, more interesting to look at. It basically tries to work with invocable objects. Okay, so functions and either free functions or member functions are invocable, and std invoke can be used to call the function and get the value back, get the tag back. One interesting point to note that some people might not realize is that a pointer to a member, even not a pointer to a member function, just a pointer to a member, is also something that's legal to use with the std invoke. If you call std invoke with a pointer to a member and an object, std invoke will treat it as if it's like an accessor or a getter to that member, which is sometimes cool. It can save some code. And that, by the way, is also another reason why it's nicer and better to use std invoke in here and not just return method open paren x close paren. Okay, so that's extracting tags. And when we go into C++20 and we have this the new type trait for is corresponding member, I can go and add this extra type of safety where I'll basically put on each and every one of my types not just its type and tag, but also a pointer to the exact member, which should be part of the header and which should be corresponding to each other. Okay, I'm using here a function template instead of a class template and the decal type in order to extract the exact intrusive variant out of it, in order to allow better a type deduction. So basically, this template function will deduce the type citizen and the member of the type citizen, and similarly for tourists, and the values themselves. And based on that, its return value will be the exact intrusive variant that I want. I'm just using a data type here. The actual function doesn't even need to be implemented. I'm just using this helper in order to ease a type deduction and to make it clear to call it. And this code can then go in still use
C++ 20 is corresponding member to add some static asserts and validations to make sure that there's no mistake and there's no case where for some reason one of the alternatives has the type in a different place and a different offset than the other. Okay, I believe that context generic lambdas can also be used for even more beauty. I think there's a small example for that later on. I won't dive deep into that right now. So that's what I have to say about like these types of inclusive pointers. But I want to sorry, intrusive variants. But I want to talk even deeper about what do we get with this mechanism, and what's the added safety, and whether we can get even more. Okay, so as I mentioned, this intrusive variant has a visit function similar to STD variant, and this visit function is as safe as a STD visit, and it makes sure that the correct tags are linked with the correct types, which is really cool. But still, there's a boilerplate in there, and there's still room for mistakes. If whoever defines the intrusive variant makes a mistake by putting incorrect types or types that are not they don't really share the same header, then it can still cause mistakes and bugs. And I think that there are potentially ways to go even better, to make things even more safe. And I think that can be done using class hierarchies. Okay, so class hierarchies, in many senses, allow us to add headers to objects. Right? If I have two classes, A and B, and both of them derive from some base class, then to a large extent, both of them have the members of the base, and those members actually reside in the same memory location in most cases, in order to allow a pointer to base to work on both objects. And that's I think really cool, and it can be a shame to not utilize it, to not make use of it. So to a large extent, when I try to look at making a union safer, it seemed to me like it might make sense, instead of rewriting this prefix in each and every alternative, why not just make all of them just derive from one single base class, and that base class will be where the actual tag is held. And once we have that, we can also use some lambdas to go and extract the correct value from each place, and I'll see an example later on. And if we were to write our variants this way, where all of the alternatives all derive from the exact same base class, it should make things even easier for the compiler to let us know if we make a mistake. We can use the base of type trait to make sure that all the alternatives indeed derive from exactly the same thing, and we can use some decal type tricks, which you can see later on, to go and access the exact members that we like. There's only one problem, and the problem is that this is totally not standard confirming. Okay, because once we introduce base classes, and the base classes have members, and the derived classes also have members, then immediately all bets are off. This is not standard layout. As I mentioned before, it's somewhat strange, because if we don't use virtual inheritance, it's quite clear that the pointer to a base should be interchangeable with the pointer to the derived, and all the members of the base should reside in the same place in memory. But still, when I try to read the standard, and perhaps I'm reading it wrong, it seems that this is not standard confirming, and having a union of two different objects, both deriving from the same base, it's still not legal to access the base member through a base pointer from the way it is. And I see Jody here in the chat adds the reasoning behind it, which is that in case of base and derived, the standard might say that the pointer to base should put the base members in some known location, but it doesn't have to be in the front. It can be maybe in the end or someplace else. This is still compiler defined, and for that reason, trying to use class hierarchies and base derived relationship in order to get extra safety in my variants or in our variants is something that sounds cool in theory,
but is not standard conforming, and really a bummer. Still, if if I share a little bit of my own experience in like the common compilers for like desktop environments or workstation environments, Clang, MSVC, GCC, usually work just as we expect them. They usually put the base class members right in front of the derived members. This all works. So if we go and try to work with this, we'll chart into undefined behavior territory, but many times it will just actually work. And I would argue that perhaps there's room to go and try to update the standard or make some provisions to allow these types of things. But it's hard to say exactly how to do it and how to not break compatibility, etc. I can think of ideas. So before diving, I want to dive in and show you some implementation that uses derived and base classes, and I want to show you that the implementation, even though I know that it's not standard conforming and it is not as safe as anything else, and you should use it with a lot of care. So before I do that, just in order to give you some indication that I'm not, totally nuts, and that there is some maybe reasoning behind my approach and my desire, I want to show you a short clip from Roi Barkan from his talk a few months ago on ACCU, where he also addresses a little bit of the question of which alternatives might usually be used in variants and the relationship among the alternatives. So let's see here, Sean.
A variant done well, where you're basically packaging things up into, anytime you have polymorphism, really what you want to be doing is packaging things up that have some similar trait that they all satisfy the same concept. And so if you have a variant that's a collection of objects that satisfy the same concepts, then that's great. Then it's just another value type, and you use it as if it were any of those objects, and everything just works.
Okay, so obviously Roi Barkan is against based and derived classes. Inheritance is the root of all evil, is the base class of evil. But even he mentions that usually when one works with a variant, the different alternatives have similarities, share the same concepts, and for that reason, there's a good chances when they will want to also share some functionality together, and that's one way to achieve that in C++ sometimes is through inheritance. So I'm running a little bit short on time, I'm afraid. So let's run through this this approach quickly. Again, we can see that I'm trying to use a union or a variant where I have this header type struct which has this type which is const, and both citizen and tourists now just derive from that header. They don't need to redefine the members. They only just pass their own tag to the constructor, and that's all there is. If I want to add more members to the header or change what I do in the header, I don't need to go and change it everywhere else in all these different classes. It all works very seamlessly. And my variant of base, I just tell it what my base class is. I will also tell it what my derived alternatives are, and I will provide it with two different lambdas. Okay, the first lambda is the one that will be used at runtime in order to check and extract the exact type. And this, by the way, is exactly similar to the get type option that I did before. So this lambda just goes to the header and extracts the type. I can also put a pointer to the member or another free function, etc., etc. The second lambda is a generic lambda, and as of I think CPP 17, generic lambdas are also const expert, even if you don't write them. And this generic lambda will actually be executed and checked only at compile time. Okay, and this is what basically extracts the correct tags of the different objects. Okay, so this is a little unclear, but during the creation of the variant of base, or during the creation of the visitation, we can iterate the different alternatives, the citizen, the tourist, etc., call a generic lambda with each of the different types. That way I will be able to extract the specific tags of all of them, and I'll be able to create the jump tables or whatever I need for the object, okay? So this, I think, is a much clearer code and much safer, and there's much less, there's no risk of having prefixes mixed up, etc., etc. But it's not standard conforming. I cannot use offset off, for example, because offset off operator is, by the way, cannot be used for non-standard layout objects. So this is something that you can use with care or not use at all. But still, I wanted to show it to you. Okay, so that's a second, like a variation of the intrusive variant that is not standard conforming, and you can use if you like. Next up, I want to talk about not just specific variants, but the arrays of variants, okay? This is, again, something that's quite common in the communication protocols and file serialization protocols, etc., where we have not just a single variant that we work with, but some stream or some array where we get one variant after the other and need to work with them, okay? And again, I want to contrast the way that C++ does it or can do it versus the common or C-style way, how in the way that these things are done. Okay, so if you want to look at an array or a region that has many variants one after another, if I go and use a vector, then basically I have a continuous region in memory where each of the members is obviously the entire variant. Its memory footprint is the same on each element. And that way I can have random access, by the way. But I can be a very, I guess, permissive, or I can be very, I can lose a little bit in terms of memory consumption, because if this first element is a citizen, perhaps the size of the citizen is smaller than the size of the entire variant. There's the second element is robot, etc., and I find myself wasting all the space for the entire variant object, although I potentially need only some of it. This causes my memory to be sort of fragmented, and it's sort of like a waste. And the intrusive variants don't help at all for this, right? Because intrusive variants, I don't have the tags, but still the entire union needs to be organized one after the other in RAM. And again, the memory is not dense or condensed. If we look at the C-style code that usually uses or passes these types of things around, perhaps because there are no STD vectors in C, or perhaps because these things usually many times arise from communication protocols, etc. The common way to work in C is actually to put a tag, and based on the tag, understand exactly what the size of and how the object looks like in memory, and jump to the next object, next entry right after it, and have things more condensed and more without any holes, etc. This is usually how the RAM looks like, or a packet looks like in many of these protocols that use tags to discriminate between different versions and variations. And because in my line of work we see these types of streams from time to time, I also wrote some helpers which I want to share with you, and you might find them interesting. So one such helper is the condensed variant iterator. Okay, so condensed variant iterator just assumes that someone placed this condensed array in memory for me. Okay, and I just want to go and iterate through it, just move from item to item, and whenever I reach an item, I have something that is similar to a constant variant that I can go and perform visitation on, or check what the active memory is. Okay, so condensed variant iterator is it's only a forward iterator. Once we go forward, we cannot move back because we don't know where to find the tag when we move backwards. Only when we move forward, we know where the header is and where the tags are. It's constant because, again, if I look at the member in the middle of an array, it's very, very risky, and it's not really possible to emplace or change the active member of any variant or any of the elements in the middle of the array, because it can really mess up the entire memory layout. Okay. Similarly, if I don't have this block of memory provided to me somehow, and I need to actually go and create it, there's also a nice like data structure called the contains-variant queue, which is like a FIFO queue. You can only place back and only pop front. Sometimes we implement it over some cyclic queue or cyclic buffer, and again we can use it in order to have it to add various objects of different types and have it all condensed in memory. And this way we can create packets or create file structures or serialization objects in a manner that is dictated by some outside protocol. And the root logic of knowing how much to jump and what's the the exact offset between each members is basically quite easy using again visitation and the fact and generic lambdas. Okay, so the visitation with the generic lambda will actually create instantiations for all the different variant alternatives. And whenever we call visit, visit will find the correct tag and call the correct implementation that knows the exact type of the object. And once we know the correct type of the object, we can, I guess, we can do a +1 on it and jump just towards its end. And after we did that, we can just do some casting back to the base class if we have one, and return that. Okay, so that's the idea, and it allows us to really go and jump from one item to another. Again, similar to the variant of base, creating these memory regions of uninitialized memory, dealing with alignment issues, dealing with these types of things is tricky. I have to tell you that I haven't looked very, very deeply into how standard conforming these utilities are. I just can say that I find them helpful, and maybe you'll find such things helpful as well. Okay, so let's have a short summary of what we've had so far before we dive into the last topic, which is somewhat different. So as I mentioned, variants are different than unions. They provide more safety. They're usually, on many cases, they are better to work with. They're easier to work with. But also, even in the real world, people don't just use unions without some tag somewhere. So it's quite common in the real world to have headers, to have tags, and the intrusive variant and variant of base are ways to try to let you have the most of the value of using variants and most of the value of a C++ type logic, while still maintaining the C-style memory layout, C-style protocols, and be compatible with outside or other languages as you work and do it. Okay, and condensed variant, as mentioned, is a way to work with the real-world streams of binary data. Okay, let's see if there's any questions or comments in the chat. Okay, so let's move on. I have a little over 10 minutes for an extra topic that relates to variants, but not directly. But I still also think you'll find it interesting. It has to do with virtualization and devirtualization. Okay, so I assume we all know what virtual functions are, and we mentioned that the variants are a way to do runtime dispatch without virtual functions. But sometimes our code base does have virtual functions, and we want to use them. And in order to get performance, there's a notion called the devirtualization that tries to to get the virtual function calls running as quickly as the non-virtual function calls. And to try and get us to thinking about that, here's a little blast from the past. I think this is from 2013. Again, Andrei Alexandrescu in a talk about this notion where he basically went and showed us how to write our own jump tables and our own virtual tables for classes instead of using virtual functions ourselves. You can see that he was promoting it because he was saying that memory usage is really important. Virtualization can be very costly, and the virtual pointers being usually 8 bytes long or 64 bits long can many times be a big waste of memory. If all of my class hierarchy maybe has 3 or 4 or less than maybe, I don't know, 256 potential alternatives, it sounds like a shame to have 64 bits of data. And what Alexandrescu tried to show in his talk a nice library or short idea of how to implement your own base classes in your own virtual tables, where the tag is only 8 bits long, and we have like a v-table of pointers to those functions, and use a virtual table by ourselves instead of letting the compiler do it for us. And when you look at this code and this information, this has some similarities to all the notions, all the things that we talked about so far, right? The tags are similar to what we have in unions. Virtual tables and jump tables for calling function is very similar to visitation. Okay, so in 2013, when Alexandrescu gave his talk, STD-variant wasn't really in sight, and I don't think he thought about it a lot. But when I saw his talk, later on in time, things looked a little bit familiar to me, and I thought to myself, yeah, first of all, obviously, we talked about the relationship between runtime dispatch and using virtual tables and variants. And this is exactly what's done here. But another thing that I tried to think about when I looked at this code is whether I can use variants in cases where I actually have virtual function calls, and then just as a way to ease performance. So in order to get a little bit of value here, I want to talk to you a little bit about the actual cost of virtual functions. Everyone, or it's quite common to treat virtual functions as something that is costly, that has performance implications and performance drawbacks. And the main topic of concern has to do with this thing called branch misprediction. Okay, and branch misprediction is a notion from the world of micro architecture and CPUs, where a CPU sometimes need to predict where the next instruction to be executed before it actually knows the information in order to make this prediction or to actually know about it. And I have to say that branch predictions indeed can be costly, but really their costs are many times very, very, very low. And the reason is that as the years went by, processors really, really improved their mechanisms for branch predictions. And that means that branch prediction rates have been going up and up throughout the years. And moreover, when the processor predictor works, it knows not just our code, but it also knows the data. It knows the current data sets that we're running in. So even if when I compile my code, I know that there's, maybe a 50% chance that the code will be executed or running in America, and a 50% chance that you're running in Asia. Whenever after the code is being compiled and we start and run it, unless I'm in an airplane, it's always either in America or in Asia. So what the compiler did not know, the processor does know. And the processor can just see that all the branches maybe are consistent, and it can learn that. It can look for patterns, not just in the program, but also in the data. And it lets it many times be much better than the compiler in trying to predict and understanding what is the next instruction to run. And compilers, on the other hand, usually only see the programs. They do not see the data, and they cannot optimize for the data. Okay, there are ways to try and mitigate these compiler drawbacks. One is profiler guided optimization, where we feed the compiler some basic benchmark or some data set and tell it to try to optimize for that. Another thing is link time optimization, where we try to tell the compiler, hey, here's the entire code base. You don't even need to guess you don't need to assume that you can have derived functions all across the board. You can look at the entire code base sometimes and understand the full class hierarchy, for example. And in C++20, we also try to let the developers assist the compiler by adding this new attribute called likely, where we can hint to the compiler what to do and how to do. And the devirtualization is the act the compiler does by using all the various tricks like profiling out optimization, looking at the code, link time optimization, and likely to try and guess what a virtual call and what a branch may go through. And it uses it for inlining, for better inspection, better rearrangement of the code. And the fact that virtual calls are usually slow is not because of the branch misprediction itself, but more because the compilers do not know to easily inline into virtual functions, to inspect them, et cetera, et cetera. Yeah, and I have a question by Rishikesh asking whether virtual function support mechanisms implementations are the same across all compilers. So as far as I remember, the standard doesn't mandate the usage of virtual tables and virtual pointers, but I believe it's still quite common, and it's considered also the quickest or the best performing implementation, as far as I know. If there are compilers that do something other than the virtual tables and virtual pointers, I think it's for other reasons, like maybe better memory usage or something. But in terms of runtime performance, I believe virtual pointers and virtual tables are considered best in class. Okay, so only a few minutes left. Let's see how we might be able to use variants to somehow to try and help our compiler devirtualize. Okay, so let's so in this case, let's imagine we have a base class with a virtual function and two derived classes. Both of them are final. This is the entire I guess hierarchy tree, unless but there might be maybe another D3 that derives from base that we don't know about. But let's imagine that I have a pointer to a base, and I know that in maybe 90% of the cases or 95% of the cases, that pointer will actually going to point to an object of type D1. Okay, so let's imagine what happens if I, instead of pointing to the object to the pointer of base, I try to point to the object with a variant that is either pointed to the base or a pointer to D1. Okay, so this variant is a little larger than the pointer itself. It holds a pointer as well as a tag. Okay, and the tag can either say that we have a D1 that we're pointing to or a base. And if we go and visit into that visitor and call the virtual function foo, then to some extent, I'm basically trying to tell the compiler, hey, you have two options. Try to treat them, I guess, identically, either going to the D1 directly, which is the final class, or just going to the base. So trying to help the compiler tell it, treat D1 as more important, more special than all the rest of the class hierarchy. Okay, so let's see if it helps at all. So this is the code that I showed you in Goldbolt. I really don't have much time, but I should say, if you're quick enough in reading assembly, you should see that didn't really help much, because what we have here is we do have this, in this case, the common case returns 750, the rare case returns 322, and here this 750 exists here inside actually an inline virtual entry of the visit function. And this jump here is the actual virtual function call for the rest of the cases, for the case that we're not in the common case, which is good. We actually got the compiler to create a nice inline version, another non-inline version. But the problem is that in order to to reach one of the alternatives, I needed to go through another jump table, which is the visitor's jump table. So I practically lost a lot of the value. But I don't really have time. The reason, I think the main reason around it is that the STD visit has to be implemented with a virtual table, has to be implemented with constant time complexity. If I go and visit and implement visit a little differently, so here I don't know if you'll have time to read it all, but here's my implementation of visit. that basically doesn't work with a jump table, but that works with an if-else. Just if the index is 1, call the first alternative, otherwise call the second alternative, etc., etc. And with this type of visitation, I get here you can see much smaller assembly code. You can basically see that all the compiler is doing is just comparing is the tag 0 or 1. If the tag is 0, I do the virtual call here in line 7. If the tag is 1, I just return 750. I completely eliminated the virtual call. I just have a jump into an inline code, which is really nice. I'm out of time. I don't see any more questions or comments. I really want to thank you. This was really a pleasure. And I'll go to the GatherTown Q&A room if you have more questions, because I think before they kick me out of here. So again, thanks very much. I hope this was clear and interesting enough. Obviously, I'll share my slides so you can go and read deeper later on. So thank you.